Hi, everybody. So now let's work through a few properties of cyclic groups. Some of these are things which we have more or less already done in some form or alluded to or assumed, and they're rather straightforward. But we're going to conclude with a real theorem, which is the assertion that if you have a cyclic group, every subgroup of that group is also cyclic. And that'll use a few actual ideas, and it'll come at the end of this little talk. But let's start with some of the more straightforward things. So the first thing we want to settle is that when we construct this subset made up of the powers of an element, positive and negative powers and zero, that it is in fact a subgroup. We've taken this for granted, and I kind of gave a little bit of a proof in the earlier video, but let's be more careful about it now. So recall that to prove that if you have a subset, if H is a subset of a group G, then H is a subgroup if two things are satisfied according to our subgroup theorems. First of all, it has to be non-empty. And second of all, if you take any two elements in the group, in the subset, you have to have AB inverses also in H. And so let's apply this to our case. So first of all, clearly, angle brackets G is not empty since G is in it. So that settles point one. And for point two, if A and B are in H, then A has to be a power of G, and B has to be a power of G. So AB inverse is G to the R times G to the minus S. Because remember that G to the minus S is the inverse of G to the S. But this is equal to G to the R minus S, and R minus S is an integer. So G to the R minus S is in angle brackets G, and therefore by this subgroup theorem, angle brackets G is a subgroup. So that's our first point. We can say a little bit more, which is that angle brackets G is in fact the smallest subgroup of G, big G, which contains little g. And by that I mean that if you have any subgroup of big G which contains little g, then it contains the whole cyclic subgroup generated by little g. So it's sort of all or nothing. If you take little g into your subgroup, you have to take all of its powers. And the proof of this is as follows. So H is contained in G, and it's a subgroup. And G is an element of H. Well, then it's certainly the case that G to the R has to belong to H for all R of the form 1, 2, and so forth, because H is closed under multiplication. So if you multiply, this is G, G squared, G cubed, and so on. And these all have to be in H because H is closed under multiplication. And similarly, G inverse has to be in H because it's a subgroup. So G to the minus 2, G to the minus 3, all the powers of G inverse all have to be in H. And the identity element has to be in H. And altogether, that tells us that angle brackets G has to be contained in H. So if you think about it, what this is saying is if you have a group and you take an element in the group, you have to also include all the powers of that element, the inverse of that element, all the powers of the inverse of that element, and the identity element. So you have to contain the whole cyclic subgroup generated by that element. Next, we make the observation that if you have a cyclic group, it's abelian. Remember, abelian means the multiplication is commutative. And to prove this, we have to show that if we choose two elements in our group G, which is generated by some element little g, that tells us that A is a power of G and B is a power of G. For integers R and S. But therefore, A times B, which is G to the R, G to the S, which is G to the R plus S, which is G to the S plus R, since addition is certainly commutative, which is G to the S, G to the R, which is B times A. And as a result, we see that G is abelian. The multiplication is commutative. And now finally we come to our first real result, which is the fact that every subgroup of a cyclic group is cyclic. And to prove this, we're going to make use of what's called the well-ordering principle. The well-ordering principle is an axiom of arithmetic, and it says that every non-empty set of positive integers has a least element. So this is typically discussed in Math 2710. It's a way of restating the axiom of induction, although maybe that's not obvious. And the way it's used typically is to, we're going to make use of the fact that if we have a set of positive integers which is non-empty, then we're going to use the least element. And intuitively, this makes a lot of sense because of the way, if we think of the positive integers as just the positive integers on the number line, it's pretty clear that if you take any subset of them, there's a smallest element. Strictly speaking, it's an axiom, but we're going to make use of it in this proof. And so let's see what goes on here. So first of all, G is cyclic, and it's generated by some element G. And H is a subgroup of G. And we need to prove that H is cyclic. In other words, we need to prove that H is a power of some element in G. And we know all the elements of G, they're all powers of little g. So let's consider a simple case and get it out of our way first. Case 1. H is just consists of the identity element. So in this case, H is cyclic because it's generated by the identity element. So the trivial group is a cyclic group in a kind of a silly way, because no matter how many powers of the identity element you take, you still have the identity element. So if H happens to be the trivial subgroup, then H is a cyclic group, and so we can treat that as done. Case 2 is that H is not the trivial group. So there is a G, well, let's call it H, an H and H with H not equal to the identity. And since G is cyclic, H has to be a power of G for some R and Z. Now there are two cases. Either R is positive or R is negative. It can't be 0, because if R were 0, then H would be G to the 0, which is the identity element, and we've ruled that out. If R is less than 0, then H inverse is G to the minus R, and H inverse is also in H. And minus R is positive. And so therefore what we know is if we define the set X to be the collection of R in Z, which are bigger than 0, and having the property that G to the R is in H, this set is not empty. In other words, there's at least one positive power of the generator of big G, which happens to lie in the subgroup H. And now we can apply the well-ordering principle to this set, and let's let T be the smallest element of X. And let's let A be G to the T. And I claim that H is generated by A. And to see this, we have to show that any element of H is a power of A. So let's pick B, any B in H. And we know that B is equal to G to the S for some S, because S is either, well, it actually doesn't matter. Now what we do is we use the division algorithm, and we divide S by T. So we know that we can write S as equal to M times T plus a remainder, where R is bigger than or equal to 0 and strictly less than T. This is called the division algorithm. It's division with remainder. Basically what we do is we take out as many T's as we can from S, and whatever's left over we call R. You have to be a little bit careful if you have positive or negative numbers here, but it's still always possible to do this with R, the remainder in the range 0 to T. And as a result, we have that B is G to the MT plus R. But G to the T is what we called A. So this is G to the MT times G to the R, which is A to the M times G to the R. And remember what we said. We said that B is in H and also A is in H. So it follows that G to the R, which is A to the minus M B, in other words, I multiply both sides on the left by A to the minus M, and I get G to the R is A to the minus MB, and this has to be in H because A is in H and B is in H, so this product has to belong to the subgroup H. Well, what have we got? We've got a power of G in H, and that power is bigger than or equal to 0 and it's less than T, but T is the smallest positive integer for which some power of G belongs to H. So R cannot be bigger than 0, because if it were bigger than 0, it would be smaller than T and it would belong to X. So R must be 0 since T is the smallest positive integer with G to the T in H. And if R is 0, we have E is equal to A to the minus MB, or B equals A to the M. In other words, our arbitrary element of H is a power of A. And that means that every element of H is a power of A. And so H must be generated by A, and H is cyclic. So in some ways, this may be the most sophisticated proof that we've done in the course so far. And it's really more about the integers than it is about the group. It really uses the well-ordering principle. So one consequence of this result is that we know all of the cyclic subgroups of the integers, all of the subgroups of the integers. If H is a subgroup of the integers, then we can choose, well, either H is 0 or choose the smallest positive integer in H. Call that n. And then it must be the case that H just consists of the multiples of n. So Z is a cyclic group. We know its subgroups are cyclic. And if you go back and look at the proof of what we just did, you take the subgroup, you take its smallest positive entry, smallest positive element, and that's going to turn out to be a generator of the group. So we will, there's still more to do with cyclic groups, but that's going to be enough for this video.